This week, my reading will be this paper. It introduced the overview of optimization across LLM. I choose this paper because it's connected directly to the hardware ideas from Flash Attention, but expand the view to the entire LLM system. So, transformer models drive today's AI progress, yet their training and inference cost keeps growing. This survey summarizes how algorithm, system, and hardware communities are now working together through hardware software co-design to make LLMs faster and move efficient across stages, from training to inference. The paper begins with a short review of transformer basics. Each transformer blocks contain a self-attention layer and a feed-forward network. In self-attention, this is the formula of self-attention from Google's paper, Attention is All You Need. So in self-attention, every token interacts with all other through query, key, and value projections, which gives a computational complexity of n squared. Multi-head attention repeats the process in parallel heads to capture different relationships, while FFN processes each token independently but still adds large matrix multiplication cost. These two components are the main targets for optimization because dominate both compute and memory traffic. So the author defined the scope of their survey as the complete life cycle of large language models: pre-training, fine-tuning, and inference. They, they specifically focus on the methods that connect software and hardware consideration, rather than purely algorithmic advances in NLP. The paper groups related work according to where optimization happens, like training frameworks, acceleration design, and system-level inference deployment. For pre-training, models like GPT or PaLM are too large for a single GPU. So parallelism is essential. Data parallelism splits the dataset across devices. Model parallelism divides layers or tensors. Pipeline parallelism sends mini batches through stages. More recently, fully shared data parallelism, or FSDP, shard both parameters and gradients across GPUs to save memories. Each strategy trade computation for communication cost, and efficient scheduling is key to keep hardware utilization high. A representative co-design method discussed is LoRa adaptation. Instead of updating all, this is the figure in Laura's paper. Instead of updating all model weight during fine-tuning, Laura inserts small, low-rank matrices and keep the original weight frozen. This reduces the number of trainable parameters by orders of magnitude, lowering both memory usage and gradient communication. From a hardware perspective, LoRa reduces the write traffic to memory and makes distributed training more feasible on small GPU clusters. It is a perfect example of algorithm system co-design. A small change in model structure brings major system-level efficiency gains. The next part of the paper survey is hardware accelerators tailored for LLM training. So GPU remains dominant because of flexibility, while TPU and custom ASICs integrate systolic arrays for high matrix multiply throughput. These accelerators must balance compute with memory bandwidth. On-chip SRAM buffers are used to reduce expensive DRAM accesses. Well, in my previous reading about flash attention, it focuses on the algorithm of designing on chip SRAM buffering. Training adds unique challenges such as gradient and activation storage, so some system recompute activation on the fly to save memory on the cost of extra compute. The overall trend is moving towards training specific chips that co-optimize arithmetics units and memory hierarchies. Okay, for inference, the focus shifts from throughput to latency and power. Quantization and sparsity reduce model size and compute. Kernel fusion eliminates redundant memory writes. In auto in autoregressive generation, caching previous key value pairs avoid recomputation but increase memory use. This is also what they talk the method they mention in flash attention. They're dealing with this storing the matrix so for the recomputation use. So efficient cache management is critical. Some systems offload rarely used weight to host memory or even to SSDs, streaming them when needed. The paper also compared cloud-based inference with on-device or edge deployment, highlighting how co-design principles help balance latency and resource limit. Okay, the paper lists several concrete inference optimization strategy and systems. So first, quantization and compression reduces model precision into int8 or even lower without significant accuracy loss. Methods like smoothquant and AWQ calibrate weight scaling to maintain stability. They are essential for deploying LLMs on resource-limited GPUs and NPUs. Second, operator fusion and kernel optimization combine multiple operations, such as attention and linear projections. They combine them into single kernel to reduce intermediate memory access. Frameworks like Fast Transformer and TensorRT LLM are widely used in both cloud and edge inference for this reason. Third, memory and data flow optimization manage the key value cache and activation buffer for efficiency. Systems like VLLM use a paged attention approach, which allocates memory dynamically and stream data in and out without stalls. DeepSeek inference applies similar optimization to handle long context at low latency. I think I will dig into this part in my previous reading because I think it's quite interesting. And finally, the paper highlights emerging edge-oriented approaches. Edge LLM and TinyChat use model partitioning and activation compression to fit large model on small devices. LLM-CAD, LLM-CAD, proposes a hardware-software co-design flow that automatically explores trade-offs between power, latency, and accuracy for on-device deployment. These examples illustrate how inference efficiency depends on aligning models, runtime, and hardware design, which is exactly the direction our lab focuses on for edge intelligence. The paper concludes the hardware software co-design will be fundamental for the next generation of LLMs. Efficiency gains will no longer come from algorithm alone. They may come from cooperation between model structures, compilers, and hardware. The authors emphasize three open directions: building energy efficient inference on edge devices, creating unified co-design toolchain that connect all layers, and developing frameworks that automatically explore trade-offs across accuracy, latency, and energy. In short, future AI system will be designed with hardware in mind from very beginning. In the future, I plan on focus on inference optimization since it is the most edge-related part of the LLM workflow. While training requires large-scale computing clusters, inference happens closer to users on mobile, embedded, or edge devices. Studies show how co-design model, compilers, and hardware for efficient inference will directly contribute to make edge intelligence more practical and sustainable. So this is my reading for this week. Thank you.